Okay, is in section 6.4 we study uniform and standard normal distribution, but before that let me first say something about continuous distribution. So we said discrete random variable takes values, finitely many values or countably many, so such as a binomial distribution. So you can represent the distribution by a histogram, okay, with bars being above the possible values. But what if in between these possible values you have a lot of other values? In that case, your bars would be narrower, and so your distribution would look, your histogram would look such so that these steps are narrower. Okay, so if you connect, let's say, midpoints of the top sides of those bars, you get a polygonal line. Okay, something like this. But if you have a distribution that can take not just these values but also a lot of values in between, then above each possible value you will have bar, and in that case bars will be narrower. And so this polygonal line in that case would have more bonds, more points to be connected. And if you take more and more possible values, your polygonal line would in most cases become smoother and smoother. And the case when you have infinitely many, or continuum many points that can that a random variable can take, that cannot be represented by some discrete histogram. That should be represented by some curve. Okay, and in that case, we, instead of talking about histograms, we talk about that limiting polygonal line. So that would be some curve. Sometimes that curve looks like a bell-shaped curve, like in normal distribution. We already mentioned normal distribution. Or it can look in any ways you want, but the only thing that matters is that the area below is just like the area of the histogram, right? Because the area below corresponds to, in discrete case, the area of the histogram, and we know the area of the histogram should be 1, and here we also have the area below this curve should be 1 for any continuous random variable. So continuous random variable is when you have continuum many, so that means any number in some interval it can be possible value of the random variable, and in that case the distribution graphically is represented. One way to represent it is using this line, and this line, this curve we call density of that distribution. So if the density looks like this, we know that the most of the values that are taken are somewhere here. Okay, and if you want to compute the probability that your random variable takes values in some interval, let's say from this point to this point, then what you would do is you would compute this area here below the density curve, and that is going to be the probability of your random variable taking the values between this number and this number. Okay, Now, as I said, density can look in any way. It just has to be above x-axis, so always no negative values, and the area below the density curve is 1. And the rest is up to you to decide. I mean, whatever curve you can imagine, like this one, as long as the area below it is 1, that's a density of some random variable. Okay? Here in this particular one, we see that the most likely values that this random variable can take are exactly those that are below these bumps. So somewhere here, and values here are probably most likely to happen, or more likely to happen than taking value somewhere here. So points in this interval are much less likely to happen than points in this interval, because the probability of taking a point in this interval is simply this area here. And the probability of taking a point in this small interval is just the area below that, above that interval, which is much less than this area here. So you see the height of the density in certain region determines or affects the likelihood of appearance of the values in that interval. So if the density is higher in this region, that means those numbers are more likely to happen. Okay? Now we will talk about uniform distribution. So uniform distribution is the one that can take values between two numbers, let's say A and B, but in some sense all points are equally likely. Now there is a problem. We are used to probability as being a value that can be found as the ratio of the number of good points, or points that verify the event whose probability we are computing, divided by the total number of points in the sample space. But there is a problem here when you have infinitely many, or actually continue many. So when you have all possible points being points between two numbers, let's say A and B. So I can see, yes, A and B. So in that case, you cannot define probability as the number of good points over the total number of points. In that case, you have to define probability using the density function, just like we just mentioned. And in the case of uniform distribution, when you want to say all points in this interval between A and B are equally likely, what you actually want to say, in fact, is that if you have interval of certain length in this region and an interval of the same length but in some other region, let's say here, then as long as these two intervals are of the same length, the probability that your distribution or your random variable will take a value in this interval is equal to the probability of random variable taking the value in this interval. So if that's what you want to say by being all points equally likely, so what you actually want to say is that all intervals of the same length are equally likely. So probability of taking a value in intervals of the same length are equally likely to happen. All right? So that implies that in fact the probability of taking a value in certain interval is simply proportional to its length. And the ratio, the proportion, is actually the ratio between the length of that interval, whose probability you are computing, over the length of the entire sample space. In this case, sample space is the interval from A to B. Okay? So let's take an example. Let me read an example from the textbook. So, power supply company called Newport Power and Light Company provides electricity with voltage levels that are uniformly distributed between 123.0 volts and 125.0 volts. So 123.0 volts and 125.0 volts. Okay, and now just a second. What's the question? So the question is, so any voltage. So the distribution is uniform. In other words, any voltage amount between these two values is equally likely. So in the sense that any interval of certain length that is a subset of this interval from 123 to 125, so here is 123.0 and here is 125.0. Okay, so any interval of certain length here has the same probability as interval somewhere else, but of the same length. Okay, so that's what it means, uniform distribution. So we have uniform distribution, and so the question is, if we randomly select one of the voltage levels and represent its value by the random variable x, then x has a distribution. So say at some moment you decide to measure the voltage that power supply company provides, and that might be any number between 123 and 125. And the question is, what is the probability that the measured voltage that you measure in that moment is has level greater than 124.5. So 120. So here is 124, and here is 124.5. So what's the probability that the voltage is above 124.5? Since you know that it's always below 125, so that means that you need to compute the probability that the randomly chosen voltage or voltage that was measured at the moment that you decided when to measure. So what's the probability that that voltage will be in this interval? About 124.5, but again it has to be up to 125.0. And so this probability is going to be equal to the ratio, as I said, the ratio of the length of that interval over the length of the entire sample space. So that means, so this interval, the length of this interval is what? Well, you just subtract the upper bound minus lower bound. So that's the length. So 125.0 minus 124.5. Of course, in this case, we could immediately say that, well, that's 0.5. But so this is a formula that works in general, divided by the length of the entire sample space. So that's from 123 up to 125, which of course we know that's 2. But in general, you would find that by just taking the difference, the upper bound minus the lower bound. So 125.0 minus 123.0. So this is 0.5 divided by 2, which is 0.25, or in other words, 1/4. This was also obvious from the very beginning when you look at this interval from 123 to 125. It's quite clear that this interval is just the quarter the entire interval. Okay, so the probability is 1/4. Okay. And now let's discuss standard normal distribution. We already mentioned normal distribution, bell-shaped curve, so the density looks something like this. And when mean is 0, so that means that the bell-shaped curve is symmetric about y-axis, so here is 0. And so when the mean is 0 and variance is 1, and also standard deviation is square root of variance, so square root of 1, so it's also 1. In that case, we have standard normal distribution. So we write in general normal distribution as like this: normal, mean mu, variance sigma squared, and when mu is 0 and variance is 1, and also that means standard deviation is 1, we call that standard normal distribution, and that random variable usually is denoted by z. Okay. Now, in fact, when I say bell-shaped curve, it's not any bell-shaped curve. There is a particular formula. For example, for the case of standard normal distribution, so the formula for this density is a function f of x equals 1 over square root of 2 pi e to the minus x squared over 2. So it's rather complicated function, but we won't discuss this function in our course. It's beyond of the scope of this course. Okay, so you just need to know that for this course, you just need to know that normal distribution is bell-shaped density, has bell-shaped density, and the mean is actually equal to the value where the highest point of the distribution is. And so when mean is 0 and variance is 1, that's standard normal distribution. Now it turns out that in nature, normal distribution is very widely appears in many situations. There is a reason for that, and that's so-called central limit theorem, which explains why normal distribution is very often appears very often in nature, and we will discuss central normal distribution shortly. But for now, we just need some basics of standard normal distribution. So here is an example. So in this section, we are going to compute probabilities that standard normal distribution falls in some interval. Okay. So here is the first problem. Scientific thermometers. The Precision Scientific Instrument Company manufactures thermometers that are supposed to give readings of 0 Celsius at the freezing point of water, because that's what it is. Freezing point of water is defined as 0 Celsius, or 0 Celsius is defined as a point where water is freezing. Tests on a large sample of these instruments reveal that at the freezing point of water, some thermometers give readings below 0, some above. So it's some kind of, if you choose a thermometer randomly, you have a random reading of the freezing temperature. So the thermometer may show a little bit below or a little bit above. So it's a random variable, and the test shows that that random variable is normally distributed with mean 0. So on average, some thermometers show values above, a little bit above, some a little bit below, but approximately equally as many above as there are below. So the mean is 0, and the standard deviation is 1, or the variance is 1. And the question is, and also assume that the reading, yes, is normally distributed. Okay, so if one thermometer is randomly selected, find the probability that at the freezing point of water the reading is less than 1.27. Okay, so what's the probability that the randomly chosen thermometer will read the temperature below 1.27? So here is, somewhere here is 1.27, okay? And the question is, what is the probability that the random variable, which is the reading of the randomly chosen thermometer, will fall somewhere here, so less than 1.27. Now if you wonder, is it strictly less than or equal to? Since it's a continuous random variable, the probability of taking just 1 point is in fact 0. So that's something that you need to get used to. If you have just finitely many values, a discrete finite random variable, each of them has positive probability. If probability of some event is 0, that means that that event cannot happen. However, with continuous random variables, you may have some events. You may have some events with positive probability. With 0 probability, but they might happen. All right. So if you choose one point, whatever point you take. So whatever point you choose, so for example 1.27, probability that x takes that value 1.27 is going to be the area below this bell-shaped curve, but above just this point, and that's just the line, and the area of the line is 0. So we need to give up on our intuition, which says that the probability being 0 means that the event is not possible. So with continuous random variables, probability equals 0. That doesn't mean impossible event. All right. It's just that the probability is 0. Okay, but in this case, in this particular problem, we are looking for probability that x, random variable x, takes value less than 1.27, and as I said, whether it's strictly less than 1.27 or less than or equal to, it doesn't matter, because the probability of including this just 1 point is you are including event whose probability is 0, so you are not affecting the overall probability. Okay, so what's the probability that x is less than 1.27? So you can read that either as strictly less than or less than or equal to. They're both the same since it's continuous. And the probability of falling into this interval from minus infinity up to 1.27 is simply equal to the area below the density curve. And so we need to find this. Now, I told you this function is ugly, 1 over square root of 2 pi e to the minus blah blah blah, and that constant e is approximately 2.7, so it's rather ugly curve, and it's actually quite nasty or very hard to compute this probability. But luckily we have tables and we have Excel, and we can use Excel command norm.dist. So norm.dist is the function. So you select any cell where you want to compute probability, where you want to store the probability, and hit equal. So that means you are telling Excel to compute some formula. Norm.dist, all right, of, and the first value is going to be this number here. Then you need to put the mean of your normal distribution. In our case it's 0, so x 0. And then you need to put standard deviation, in our case is 1. And then you need either true or false, or either 1 or 0. I will place 1. 1 means you want cumulative distribution, so up to that point x, all right? If you place 0, then it's going to compute the probability of exactly x taking value little x. In case of any continuous random variable, that's 0, okay? So we were always going to compute just cumulative, so it doesn't make sense to compute point mass. All right, so in our case, this is equal, we are going to have norm dist of 1.27, 0, 1, so mean 0, variance, standard deviation 1, and this one says yes, cumulative. And when you do that, Excel will give you number 0.897, 958. Okay. Now, next problem is to compute the value. Compute the probability that a randomly chosen thermometer, so the same setup, the same problem, the same distribution, but what's the probability that the randomly chosen thermometer at freezing temperature will show a temperature less than negative 0.52 Celsius. Okay, so now the question is, what's the probability of the random variable falling below this interval? So that means you need to find this area here, this small area. And again, you would select a cell in your spreadsheet in Excel and have norm dist of, and now your x is going to be negative 0.52, 0, because we still have standard normal distribution, so mean 0, standard deviation 1, and yes, cumulative. We want cumulative probability, so that means the probability of taking value up to negative 0.52, right? And the Excel gives you number 0.301532. 0.301532. Okay? So example 1, example 2. Now, example 3. Example 3 is, what is the probability? So I'm going now to change it to example 3. What is the probability of getting a value in between negative 0.52 and 1.27. All right? In other words, what's the probability that the randomly chosen thermometer will, at the freezing temperature, show the value, show the temperature between negative 0.52 Celsius and 1.27 Celsius. Okay? So now what you can do is you can use the previous two examples. Okay, so you want the area, this red shaded area, to compute. What you can do is you can compute this using you can compute this red shaded area as the difference of the area from minus infinity up to this point. So that means this part plus this part. So blue area plus red area. I don't know whether you see. So this is supposed to be blue, and this one is supposed to be red. Okay? So you want the your goal is to compute this red area. That's the probability of the random variable falling into this region, into this interval. Okay? It's going to be, so that area is going to be the area blue plus red minus the blue area. So why did we do in that way? Because blue plus red is nothing but this value, norm dist of 1.27. That's the probability of falling below 127 minus the probability of falling below 0.52. That's this blue area here. So that's what we computed here. Okay? And so just subtract this value minus this value, and that's 0.596426. So it's going to be norm dist of 1.27,011 minus norm dist of negative 0.52,011. Okay, so it is equal to, so as I said, it turns out to be 0.596, 426. Okay, so that's the that's your probability. Now, in MyStatLab, you also have tables. There is a Z table, so table for standard normal distribution for negative values. So for blue areas, when you have the cumulative distribution up to some negative value, okay, and you also have a table for cumulative distributions for up to some positive value, okay. And in my other video, I do some examples where I use that table, so you should also check out that because it's anyways obligatory for you to watch all the videos. Okay, so that's the second part of that video. Is second part of the section 6.2. Okay.